Hello everyone and welcome to our new video. In this video, we will be conducting a loan approval analysis where we will be exploring the different factors that influence loan decisions, basing our analysis on a credit institution. There are different things that we are going to perform under this analysis. I'm going to be listing the major ones that we will be tackling under this analysis. And the first one will be on loan application segmentation. Under this analysis, we will be grouping the different types of loan applicants according to the income they are making, also according to the number of dependents, their education level, as well as the type of employment. Also, under this analysis, we will be conducting the applicant's loan approvals. Under this, we will be determining the rates of loan approvals according to different features. Some of these features include the levels of education, the employment status, as well as the number of dependents. We will also be conducting the loan approvals where we will be considering the different types of CIBIL score for different applicants. Another type of analysis that we will be conducting will be the correlation analysis. Under this, the main objective will be testing for significance depending on the features that we will be employing in this analysis. Some of the features include income and assets. So under this, we will be determining if applicants' income has a correlation to the types of assets they possess. Another thing will be the asset value influence on loan amount, as well as the assets value influence on a loan approvals. Other types of correlations will be between income and loan amount, the CIBIL rating, we can also say the CIBIL score and the loan status, and lastly, the loan status and self-employment. Under this analysis, we will also be, and also under this analysis, we will be using a logistic regression. This is a machine learning algorithm. So we will be using the logistic regression to build a predictive model, which will take the loan application features. These features are some of these features are what we have already discussed, and we will use these features to predict the likelihood of a loan approval. That means determining if a loan gets approved or rejected. And lastly, under the logistic regression, we will be determining the accuracy of our predictions. So in briefly, this is what we will be discussing under this analysis. So do stick by until the end, and please help us spread the message. Consider subscribing to our channel. We are welcoming you to our community. You can also like this video, and you can also leave a comment behind, because we will very much like to hear from you. So without further delay, let's jump right into our working environment and start working on this task. Welcome. We will start by importing the Python libraries. I'm going to first import the pandas, numpy, matplotlib, and CIBIL Python libraries. But as we progress, I'll be including other libraries or models, and that will depend on the type of analysis that we will be carrying on. But for the start, let's just import the most common. So after typing this, I'm going to run this cell, and when it's complete, we will have imported our Python libraries. So the next thing after importing our Python libraries, I'm going to load the CSV file. So while loading the CSV file, I'm going to use the read CSV function from pandas. So this is the function that we are going to use while loading our dataset. So inside the brackets, I'm going to pass an argument. In this case, will be a combination of the file path, that means the file path of our CSV file, as well as the name of our dataset. So I will shift to where I have saved my CSV file or our dataset, then copy the file path. This is where I have saved my file. So I'll just click on this tab up here and copy the file path. So this is the file path. So it's inside the quotation marks. So that means it is being considered as a string. Then I'll go ahead and add the document name or the dataset name. So it's a CSV file. So I will add the name of the file. Then I'll end with a suffix CSV to denote that it is a CSV file. So after that, I'm going to save all of this inside a variable name. I'm just going to call my variable df. So in Python, backslashes are often used to escape special characters. However, in a file path, backslashes are often used as part of the path itself. So in this case, I want the backslashes to be considered as characters and not to be used as escapes and not to be used to escape special characters. So to avoid that, I'm going to add a letter R just before the opening quotation mark. So after doing that, I'm going to print an output using the head method, the first 5 rows of our data frame, just as a confirmation that we have successfully loaded our data set. When I run this, you can see that we are getting an output, and the output is partial or part of our larger data frame. After loading our CSV file, we will then move on to data descriptives. In this case, we are going to check for the shape of our data frame. By checking for the shape of our data frame, I'm going to use the function, I'm going to use the info method. So when I run this, as you can see, we are getting an output, and from the output, we can locate the range index. So the range index shows the total number of rows in our data frame. Also from this, we are also getting the columns and the column labels. The column labels meaning the names of the columns in our data frame. Also, we are getting the null count. When we say the null count, these are the non-missing values in our data frame. So if a column has a significantly lower null count compared to the total number of rows, the range index, that means it might indicate presence of missing data in the columns. And also we can get the type of data types in the various columns. And as you can see in the first 2 columns, we have integers, objects, object as a data type, that is a string. So basically, this is how we check for the shape of the data frame. The next thing, this is also another method for having a general overview of our data frame. We are going to use the describe method. So when we use this method, what the output from using the describe method is that it returns a description of the data in the data frame. And by this, we are getting information about the count. Also, we are getting information about the count. And as you can see, the count in each column is similar to what we had seen earlier. Also, what we are getting is the mean, the standard deviation, the minimum value, the percentiles, that is the 25th, 50th, and 75th percentile, and also the maximum value in each column. So that's what we get when we use the describe function. And another thing from the describe method is it only, by default, it generates descriptive statistics basically on the numeric columns in our data frame. As you can see, we have skipped the columns that contain strings. Data cleaning is very important in data analysis, and it is a process of identifying and correcting errors, inconsistencies, and inaccuracies in your data sets. And by doing so, we are going to improve the data quality and the reliability of our results. So generally, there are different ways, or rather, there are many ways of cleaning your data set. But in our case, our data is relatively clean, so we won't delve into more processes of data cleaning, but I'll highlight just a few. The first thing that you're going to consider under data cleaning is checking for duplicates. Under checking for duplicates, I'm going to use the function, I'm going to use the method duplicated, and inside the brackets, I'm going to pass a parameter that is keep. What this function does is that it's going to count all duplicated rows in our data frame, and it will give us a sum indicating how many duplicated rows are present in our data frame. When we run the cell, we are getting 0, indicating that our data frame does not contain any duplicated rows. If we could get a value greater than 1, then that means that our data frame contains duplicates. By so, we will then move on to the step to a further step where we will have dropped the duplicates. Another thing that I noticed with our data frame, we look under the description of our data frame, we can see that the residential asset value column, the minimum value is a negative value. A loan applicant can either possess an asset or may not have an asset. So it's either possessing an asset or not having an asset. So we are going to clean that, meaning that we are going to convert the values in the residential asset value column into absolute values. That means we are going to remove any negative values in that column. So in that case, what we will be doing is that we will be converting values in a specific column, that is the residential asset value column, to absolute values. And this is how we will do it. We are using the absolute method in pandas. So we are applying the absolute method targeting the residential asset value column, and our output from that manipulation, we are going to save in the same column, so we are not changing the names or the name of the column. I would like to check if the process was successful, and I will do this by counting the number of negative values in the residential asset value column. So this is just a confirmatory test to see if our original code snippet worked. So we want the values in the residential asset value. So we are looking for values that are less than 0. And then we will sum them to determine how many values are less than 0. So I will run this cell. When we run this cell, we are getting an error, and we can see the keyword error. The key error comes from the residential asset value, and this maybe takes us a little back when we were checking for the shape of our data frame. So there's something that I realized when you look at the columns. The first column, loan ID, is aligned a little bit left than the other columns. For the columns from the number of dependents to the loan status, we are having some white spaces. If we insert the white spaces for this case, and we run again this cell, you can see we are getting an output which is 0, indicating that there are no negative values in the column residential asset. The next thing that I'm going to do is that I'm going to remove the white spaces in each and every column in our data frame, and also I'm going to remove any white spaces from all values in the data frame. this method is applied to each column name to remove any leading or trailing white spaces. So we are, in short, stripping the white spaces at the beginning and also at the end of the column names. So while removing the white spaces from values in the data frame, I'm going to use the lambda function. So the lambda function checks if x is a string, and if x is a string, the strip method is applied to remove the leading as well as the trailing white spaces. And if the value is not a string, it remains unchanged. That's why we have included the else block in this case. By these two methods, we are going to remove the white spaces in the columns and also the white spaces in the values in our data frame. So I'm going to run this cell, and you can see all our columns are aligned by starting from approximately the same position. That means we have eliminated the white spaces. And when I use the describe method, I will check if the residential asset value column, if they as you can see, the residential asset value now, the minimum value is 0. After this, we can then move on to something else. We are then going to move on to adding some new columns in our data frame. This is a loan approval analysis dataset. So we are looking at this dataset and determining factors that contribute to a loan being approved or rejected. And basing on the columns we currently have, I think we need to add some other columns. These columns will be very critical or very vital when conducting exploratory data analysis. One of the columns that we are going to add is the CIBIL rating column. CIBIL score is often used synonymously with credit score. That means they almost mean the same thing. A credit score is based on a credit report, and it is often used to represent the creditworthiness of an individual. So in our case, we will use a CIBIL score, and it will range between 300 and 900. Lenders such as banks and credit card companies often use credit score to evaluate the potential risk posed by lending money to customers. So in our case, from between 300 to 549. So if any loan applicant is having a CIBIL score between 300 and 549, we will label that customer to be having a poor CIBIL rating. And if it's between 550 to 649, we will label the customer as having an average CIBIL rating. Also, between 650 to 749 and between 750 to 900, we will label the customers to be having good and excellent CIBIL rating, respectively. So we are going to transfer this information to our data frame, where we are going to create a new column. So the first column that we're going to add is the CIBIL rating column. So while adding this column, I'm going to use functions. So I will be adding a CIBIL rating column with the values poor, average, good, and excellent. So we are going to first define the name of our function. So def. And when creating functions, we usually have places where we pass our parameters and arguments. So for this case, inside the brackets, we are going to pass a parameter, and this parameter, we will call it a value. So this value, in essence, it means the CIBIL score value. So because we will be targeting the values in the CIBIL score. And the block of our function, I'll be using the conditional statements, that is the if-else statements. What I'm saying with this statement is that if our value is greater than or equal to 300, but it is less than or equal to 549, we are going to return a value poor. We can just copy this and repeat it again. And in our next range, where the CIBIL rating is average, it's between 550 to 649. So if our value, that means the CIBIL score, is between 550 and 649, we are going to return average as our value. In our next range is between 650 to 749, and here we'll label them as having a good CIBIL rating, and the next will be 750 to 900. So we'll label them as having an excellent CIBIL rating. And then after this, we are going to include the else block. So if a client or an applicant does not feature within the 300 metric to the 900 metric, we are going to return, let's say, error. So that means the CIBIL score is not within 300. It's not within the metrics that we have set, that is between 300 and 900. So when it turns an error, maybe we need to go and check if the CIBIL score is between our ranges of 300 and 900. On the conditional statements, the if-else statement. So the first block, we are using the if, but the other one, the succeeding ones, we are using the elif. But we are ending with the else statement. So after we are then going to close off our function. So we are then going to apply the CIBIL rating function to each value in the CIBIL score column. So we are going. So the column that we are going to target is the CIBIL score column. Then we are going to apply the CIBIL ratings. Okay, the CIBIL rating function to each value in the CIBIL score column. So I'm going to use the apply function. So dot apply. Then specify our function. Then after applying this, we are going to save our output in a new. So the new column that we are going to save our results is the CIBIL rating. So it's the CIBIL ratings column. So I'll then just to display our output to see if we have added the CIBIL rating column. So when I run this, we are getting an output, and you can see that the CIBIL ratings column has been added to our data frame. For example, for the first applicant, they have a CIBIL score of 778. So 778, they fall within this range between the 750 to 900. That means they will be having an excellent CIBIL rating. And as you can see under the CIBIL rating column, we have labeled them to be having an excellent CIBIL rating. So that's how we add a column to our data frame and populate it with the necessary information. So that's the first column that we will be adding in the data frame. The next column that we will be adding So the next column that we will be adding the income levels column. So basically what we are doing here, we are going to group the loan applicants in terms of income they make. Then we will classify them according to various groups depending on the income levels, and create a new column and populate that column with the necessary information. That information pertains income levels. So we are going to group income by applicants. So we are going to group income by applicants to different levels. And those levels are either low income, low middle income, upper middle income, and the high income levels. So when we look at the income range, we are saying that between 100,000 to a million, that's the income per annum. In terms of the income levels, we are going to group the applicants in the low income levels, and between 1 million and 1 to 4 million, we are going to group them to lower middle, and before 4 million and 1 to 7.5, we are going to group the applicants in the upper middle income levels, and between 7.5 and 1 to 10 million per annum, we are going to group those loan applicants to be in the high income levels. So we are going to, the first thing that we did is that we defined our function. So our function name, we call it income levels. And or if the value of the income that the applicant is making per annum is between 100,000 to a million, then we are going to return the value low, meaning that the customer is in the lower income levels. Else or else is if the income is between 1 million and 1 to 4 million, they are in the lower middle. Also, if they are between 4 million and 1 to 7.5 million, they are in the upper middle. If they are between 7.5 and 1 to about 10 million, we are going to group the customers to be in the high income level. Else, we are going to return something like very high income. And so in our data frame, we are going to target the income annum column. As you can see, this is the income annum column. So that will be supplying our values, which we are considering them as our parameters in our function. Then we are going to apply our function. So we created this function. So we are going to apply this function to the income annum, targeting the income annum column, and the results from that computation, we are going to store that into the new generated column. That's the income levels column in our data frame. So after we complete that, I'm going to print the output from that manipulation. And when we print that, we can say that we have included the income levels column in our data frame, and we have also populated that column with the necessary information. Since this is a credit institution, that means it is offering loans. We are then moving on to group our loans into different categories. So generally, we have 4 categories of different types of loans, depending on the amount. And those are the bronze, silver, gold, and platinum. By using loan range, we are going to classify the loan amounts that were requested by different clients. By addition of the loan rating column, we are going to be grouping loan amounts as either bronze, silver, gold, and platinum. We are just going to repeat the same thing as we did earlier. So this will be the function that I'll be using. It's just similar to what we did earlier. So between 100,000 to a million, bronze, then silver, gold, platinum. All right. Then we are going to close off our function. That means we are going to apply our function loan rating, targeting the loan amount column. So we are targeting this column. This is the column that stipulates or indicates the amount applied for by the different applicants. So we are going to target the loan amount column. Then the output from that manipulation, we are going to save in the loan rating column. This will be a new column that will be created in our data frame. Then we are just going to display. And as you can see, we have added the loan rating column in our data frame. All right. So moving on, there is also another column that we will be expected to add. That is the long-term range column. And from this description, you can see that we are going to group loan terms into either short-term, intermediate, and long-term. So a loan term that is between 0 to 7 years, we are going to regard those loan terms as short-term loans. And loans between 8 to 14 years, we are going to regard them as intermediate loans. And loans between 15 to 20 years, we are going to regard them as long-term loans. Again, we are going to use this information and with what we have already learned to create a new column and populate it with the long-term labels. So we are grouping loan terms as either short-term, long-term, or intermediate. So this is how we will do it. Then just change this to ELIF. Earlier on, we saw that between 0 to 7 years, those are short-term loans. Between 8 to 14, those are intermediate loans. And between 15 to 20 years, those are long-term loans. And else we return unknown. Again, we are closing off our function. Then we are applying the results from our function, targeting the long-term column, then populating our newly created column with going by the name long-term type. Then we'll just maybe print the results from that. And as you can see, this is the long-term type column with the necessary information. Last column that we're going to add in our data frame will be according to the number of dependents. So we are categorizing loan applicants according to their number of dependents to either low dependents, moderate dependents, or high dependence. So again, according to the number of dependents, so we are either grouping according to the number of dependents. So this is the dependent class, which is either low. So this is the dependent class, which is either low, moderate, or high. And between 0 to 1, you can regard them as having low dependence. 2 to 3, we can regard them, the loan applicants, as having moderate number of dependents. And between 4 to 5, you can say high dependence. So we're just going to replicate what we did earlier. So this is the last column that we will be adding in our data frame. And this represents how we perform some further manipulation in our data frame to either add a few other columns in our data frame. These columns will be very important as we proceed forward. They are very necessary in terms of because of the different types of analysis that we will be handling in the exploratory data analysis. So in the exploratory data analysis, the first thing that we are going to do, we are going to start with the customer segmentation. We are going to group applicants in terms of the income. So we are going to determine how many applicants fall under the low income bracket or the high income bracket. Also, we are going to classify them according to the number of dependents, how many applicants are in the low dependency level class, or moderate or high. Also, in terms of education level, as you can see, we have the graduate and non-graduates, indicating that how many loan applicants are graduates and how many loan applicants are not graduates. And we're also going to do the same for the type of employment. So let's start with income. So with this, you're going to grouping customers according to their income levels. So we'll be targeting the newly created column, that is the income levels column. You're going to count the values in this column, and I will reset the index because we are generating a new series and print the outcome. When we print the outcome, so this is a new series that we are creating. Another way that you can print the outcome is using the add function. So as you can see, we have sorted our information into a new series. Our new series contains information about the income levels. But we have not correctly labeled our columns. So I'm going to label the columns in our new series. So while renaming the columns, I'm going to use the rename function. So that's the rename function. I'm going to target the columns. So I'll pass in an argument that will be columns. Then I will use a set to define the original name of the column and pass a new name for the column. We are going to change from index to income level, and instead of the column income levels, we are going to change that to number of applicants. So instead of index, we are using the income level. Let's say instead of index, we're using the income levels, and instead of the income levels, we're changing that to number of applicants within the different income levels. Then we are going to run this cell. So when we run, you can see that we have successfully changed the names of the columns. Maybe we can plot a pie chart to represent this information visually. So we can use a pie chart to visualize this data. So by plotting a pie chart, we will be using the matplotlib library. So plt.py meaning a pie chart. Then I will recall the variable containing our data. So that's the income. Then I will supply the values. Then the labels. So the labels will be the income level column. Include a title for our pie chart. Then we will display our chart. When we run this, we get the output is a pie chart, which is displaying the number of applicants in each income level. So the upper middle contributes to about 36% of our applicants, followed by the lower middle at about 30%, then the high at 24%, and the low at close to 10%. So that's how we segment our customers or applicants in terms of income. Another metric that we are going to use, segment customers according to the number of dependents. So we just repeat the same. So dependents, then dot value counts. Then I will set my index. Then just as we did earlier, I'm going to changing the names of the columns. Then we will print our output. So that's the segmentation according to the number of dependents. You can go ahead and plot a pie chart. Another thing that we are going to segment according to education. It's just almost similar thing that we will be doing. So I'll just, because I've already done this, I'll just copy what I did and paste it here and explain a little bit what I did. So we are sorting data, focusing on the column education. So we will be counting the unique values in the column education. And after we generate a new series, we will reset the index. And this line of code, we are just changing the titles or the column names. Then we will print out our outcome. So as you can see, in terms of education level, for graduates, we have about 2,144 applicants who are considered as graduates. And in the class of applicants that are not considered as graduates, those are the non-graduates. Those are 1,125 applicants. The last type of segmentation that we will be doing is we'll be segmenting in terms of employment. So when you are segmenting in terms of employment, we are focusing on the column self-employment. So it's either yes or no. So when we run this, again, you can see we have segmented according to employment. For self-employment, those who are self-employed, 2,150, and those without self-employment, 2,199. So this is just the overall loan approval rate. So we will determine that. In terms of the loan approval rate, we are going to target the column loan status. So it contains the data in terms of approved and rejected. Just as we did earlier, we are going to group targeting the loan status column. So we are going to, so I've used variable loans, and we are going to use determine the loan status column. So we are going to count the values and reset index in our new series. Then I will directly change the name of the columns and print out the output. When we run, you can see that in terms of loan approval and rejected, a total of 2,656 loans were approved. Let's plot a pie chart to visualize this information. So I'll just use the same cell. So plt Then in terms of labels, and we supply a title for our chart. So when we print out the output, as you can see, overall, we can report that the overall rate of loan approval is at 62.2%. So you have a 62% chance of getting a loan if you apply with this institution, and you have a 37.8% chance of your loan being rejected. So we'll move on to calculate the loan approval rates according to factors such as education status, also in terms of the employment status, and also according to the number of dependents. So we are going to start by loan approvals according to the level of education. So the first thing that you're going to do, you're going to group our data by focusing on the education column as well as the loan status. And after grouping our data, we are going to count the number of unique occurrences. We are going to use the group by method in pandas. Inside the brackets, we are going to pass arguments. So the arguments will be the names of the columns that we are targeting. So what we are going to do with this, we are going to count the unique occurrences. So we are going to determine the total number of elements in a series in the series. So we are going to use the size function, and after generating the new series, we are going to reset the index. With respect to the column education, we're going to filter the loan statuses to only include the approved and rejected. So the loan status is, so it's either approved or rejected. Then after this, we are going to print our output. So this is the output. As you can see, we have the column education. So for graduate and approved, there were 1,399, and for graduates rejected, 805. For non-graduate approved, 1,317, and for non-graduate rejected, it's about 808 applicants. To clearly visualize this information, we are going to use, when creating a heat map, the first thing that you need to create is a pivot table. So I'll start by creating a pivot table. A pivot table generally has we need to define the index, we need to define the columns, and we need to define our values. So in our case, education will be our index. The loan status will represent our columns, while the column labeled as 0, so I've not changed the name of the column. So I'll show you later how we can change the names of the column. So the 0 column will represent our values. So as I said earlier, index will be education. So in our pivot table, I just want to represent those figures in terms of percentages. We are going to sum our values with respect to the rows in our pivot table. So I'll say row totals. So the totals in the rows in our pivot table. So pivot. So when using the sum function, I'm going to pass in a key parameter. Our parameter axis equals 1. Then after summation, I'll want to represent these values, the values in this column. I want to represent those values in percentages. The variable. So in this variable, we are going to divide each element in the pivot table by the corresponding row total from the row totals variable. So by calculating the percentages, the result from this will be a new series where each cell contains the percentage of approved or rejected loans. So I'll close this by multiplying by 100. So the multiplication by 100 converts the fractions into the percentages. So with the results obtained from the pivot table, I'm now going to move ahead and plot the heat map. So the first thing with the heat map, I'm going to first plot the figure or define the size of my figure, the size of the heat map. So the figure size or the size of our figure will be 8. Let's say 6 by 4. So that will be the size of our figure. Then I'm going to create the heat map. So I'll be using the Seaborn library. So SNS, then heat map to define that, to state that we are going to create a heat map. So we are going to use the data in the pivot table while creating the heat map. So by saying annotate true, we want the columns and the rows in our heat map to be annotated. That means to have value. Then the format. So that will be, I'll say I want to 1 decimal places. Then the color mapping. I will use the Coolworm. Then line width. So labeling the heat map. So the heat map will be will have a title loan approvals by education, while on the x-axis will be the loan status, either approved or rejected. So that will, and our y-axis will be labeled education status. And with this heat map, we can see we are grouping our table, the education versus loan status. So education versus loan status, and we are calculating the loan approval rates according to the level of education. So for graduates, they have a 62.5% chance of their loans being accepted or being approved, and a 37.5% chance of their loans being rejected. When we compare between the graduate and the non-graduate, both are at 62%. So technically, we can say that there is no significant difference between loan approvals for both graduates and non-graduate. So we are going to calculate loan approvals according to the type of employment. So the first thing that we are going to do is just similar to what we did earlier. We are going to group the data according to the employment status and also focusing on the loan status column. So this is how we group our data according to employment status and the loan status. Then after this, we are going to filter to include the approved and rejected loans. So we are going to filter to include the approved and rejected loans whilst focusing on the loan status column. So in the loan status column, we are going to check for instances of either approved and rejected. Then from this, we are going to print the outcome. So this is the output from that. But in this case, I'm going to change the name of the zero column. dot rename. So we are using the rename function, so specifying the columns. So that's we are going to change from 0 to, let's say, total. So that means the total loans either approved or rejected. So when we run this again, so when you run this cell, so we have changed the name to total. So in the totals column, we get the number of the loans either approved or rejected for the type of employment. So for this, again, we are going to also plot a pivot table. We are also going to create a heat map. So we are just going to follow the same thing as we did earlier on. So I'll just copy this. Then I'll paste it here and change whatever it's necessary. So instead of education, we are going to use the variable employment type. On the values, we are going to change to total. Again, we'll be summing so this will remain the same. And again, we'll also be calculating the percentages. Again, this line will remain the same. In terms of creating the heat map, I think everything will remain the same. But when it comes to labeling, so this will be loan approvals by type of employment. X label will remain the same. The Y label, I will change the Y label. So instead of reading education status, we will change it to employment status. Again, so this is the output from that small analysis. So this is the heat map that is representing the loan approvals by the type of employment. So employment status is either yes, meaning self-employed, and no, meaning the applicants are not self-employed. And as you can see, we are almost getting a similar value as we did earlier. It's in the range of 62%. For the rejected, it's about 37%. So the next thing that we are going to determine is the loan approval rate by CIBIL rating. Earlier on, we added the CIBIL rating column where we either grouped loan applicants as either having an excellent, good, poor, or average CIBIL rating. So we are going to determine the influence of this CIBIL rating on loan approvals. We are expecting that having an excellent CIBIL rating, maybe you'll be having a higher percent rate of loan approvals, while having a poor CIBIL rating, you will be having a lower rate of loans getting approved. So the first thing that we are going to do is that we are going to group our data according to the CIBIL rating and the loan status, as well as we are going to count for each combination. So we are going to group by, so df dot. So we are going to group according to the CIBIL rating as well as the loans status. Then because we are going to count, I'm going to include the size, and because we are creating a new series, I'm going to reset the index. After grouping our data, I'll then move on to rename the column, because we know one column, mostly the last column, usually has 0. So I'll be renaming that column to total. Then after renaming the column, I will print the outcome. So this is the outcome for our result. loans approved for average CIBIL rating were 681, while 2 were rejected. For excellent CIBIL rating, the loans approved were 1050. We expect a higher approval when you have an excellent CIBIL rating, while for good approved is 740, rejected is at 5. So 5 loans applications were rejected. For having a poor CIBIL rating, 185 loans were approved, while 1,600 loans were rejected. So technically, when you have a poor CIBIL rating, we expect that less of the loans will be approved. So we are going to represent this information in a heat map. And as we did earlier, the first thing that we are going to do is we are going to first create a pivot table. So this is the pivot table. So the index is represented by the CIBIL ratings column. So CIBIL ratings column, while the columns will be the loan status, so either approved or rejected, while the values will be from the total column in the new series. After plotting the pivot table, we are going to calculate the approval rates. When calculating the approval rates, the first thing that we are doing is that we are summing the total number of loans that were approved and the total number of loans that were rejected. After summing, we are dividing that with the number of loans that were approved, then multiplying that by 100 so that we get the percent of the percent loan approvals for each CIBIL rating. Then once we are done with that, we are saving the output or the results from that calculations into a new column in the pivot table, and we named it as approval rate. After calculating the loan approval rates, what we are going to do next is plotting the heat map. So we are creating the heat map and defining the size of our figure, then plotting the heat map. So what we are focusing on, these values. So that's what we are passing it. So that's what we are using in the heat map. Then we are annotating, using 1 decimal place for the values in our heat map. This is the color map and this is the line width. So these are the labels of our plot, and when we display our plot, this is how it looks. So this is a little bit different as you can see, it's a little bit different with what we were doing earlier. So what we are doing, so for this case, for the interpretation from this chart is that in our dataset, if you have either average, excellent, or good CIBIL rating, you have a 99% chance of your loan getting approved. While if you have a poor CIBIL rating, you only have a 10% chance of your loans getting approved. Under correlation analysis, the first thing that I think is very important is to plot a correlation heat map. So a correlation heat map is a representation of the correlations. That means the relationships between numerical variables in our data set. So I'm going to first plot that so that we can visualize the relationship in the numeric columns in our data frame. So I just want to focus on the numeric columns in our data frame. That's why I'm passing an argument in the correlation function that it should only focus on the numeric columns. So after this, we create the heat map. So when we run this cell, so the values in the heat map represents the correlations between two variables. So the positive values indicate a positive correlation meaning that as one variable increases, so does the other. While the negative values indicate a negative correlation, meaning that if a variable is increasing, the other variable tends to decrease. And the value that is very close to 0 indicates that the correlation between the two variables is a weak correlation, or basically you can say that there is no correlation. So the diagonal line of the heat map usually shows the correlations of variables with themselves. So as you can see, the loan ID is so one is just a correlation between same variables, and technically this will be a perfect correlation. So the important types of correlations that we will be assessing, the first one will be in terms of income and loan amount. So the correlation between income and the loan amount is 0.93. It's a strong correlation, meaning that if income increases, so does the loan amount that an applicant is allowed to borrow. Another correlation that we can show in this heat map is for example, income per annum and the value of assets. So we can also check for that type of correlation. So when you look at the income per annum, this is the income per annum, and the value of asset, let's say residential, commercial, luxury, and bank assets. So you can see between income per annum and the residential asset, you can see it's 0.64. You can say it's relatively a higher correlation. So there's a correlation between income per annum and residential asset, which can be interpreted as if you're making a lot of money, then the chances of owning a residential asset is also high. It's also 0.64 for residential asset, and it's 0.64 for commercial assets. So it's just the same type of interpretation. When you look at the income per annum and the luxury asset value, we have a strong correlation. So I'll start by grouping the assets together and the income together. So with this line of code, we are grouping assets together. So in terms of assets, we have the residential assets, commercial assets, luxury assets, and bank assets. So we are going to perform a correlation with income. So when we are calculating these correlations, these are Pearson correlation coefficients that we will be calculating or will be obtaining from the correlation heat map. We have sorted our data to a new series, as you can see. Now, from this, it's very easier to analyze the types of correlation. Now, when we look into correlations in terms of income, now as you move across and along your table, you can now see that when we compare income per annum with asset value, so between income and residential asset value, you can say we have a correlation of 0.6, and between income and commercial asset, we have a correlation of about 0.64. All right, so this is how we can sort our data into a tabular form. So it's very easier with this when you have sorted your data into a smaller series. So this was the correlation between asset value and income. We can also sort our information to determine the correlation between asset value and loans. So I'll just copy this. So we are determining the correlation between asset value and loan. So the only thing that will be changing, the assets will remain the same, but instead of income, we are going to change to loan amount. While for income, we can just say loan. So assets will remain the same, but we'll change the income to loan. and then we print out our outcome. So with this table, we are just comparing the assets with loan amount, and as you can see, we have strong correlations. So technically, from this analysis, using the Pearson correlation, we can say that assets have a strong correlation with loan amount. So that's how you can sort your data from the correlation heat map. So in our next analysis, we are going to determine asset value impact or influence on loan approval. So the first thing that we are going to do, we are going to split the data into two groups based on loan status, approved or rejected. So the first one, we are going to split the data according to approved loans. So approved. And the next thing that we are going to do, we are going to separate according to the rejected loans. So after splitting our data into two groups, we are then going to perform a t-test. And since we are comparing asset value and loan approval, the first thing that we are going to specify is the assets. So our assets include the residential assets, the commercial assets, luxury assets, and bank assets. Then from this, while performing a t-test, I'm going to use the for loop. So for columns in assets, so we are performing a t-test. So t-test, and this is t-test is an independent t-test. So from the t-test, what we are going to print. So I'm using f strings. From our results, we'll be printing out a t-test, a t-statistics, as well as the p-value. So this will print out the t-statistic, and this will print out the p-value each column, meaning each asset column. Also, I want to include the conditional statements. So this is the conditional statement that we will be including in our analysis. We are setting the conditional statements to check if the p-value is either less than or is either less than or greater than 0.05. That is at 95% confidence level. So if p-value is less than 0.05, it indicates that the difference in asset value between the approved and the rejected loans is statistically significant. While if the p-value is not less than 0.05, meaning that it is greater than 0.05, it will suggest that there is a difference between the asset values between approved and rejected loans. So when I run this, we are getting an error. So what we have not done, we have not imported the t-statistic module. So I'm going to import the t-statistic module so that we are able to conduct this analysis. I'm just going to import all the modules that will be necessary for that analysis. So I'll head back the first cell. So from here, I'm going to import these modules. So these modules are from SciPy. For the t-test, we'll be considering this module. So I will import this module by running each and every cell. So I will restart and run all. This is the results that we are getting. So when we compare the residential asset value to our loans being either rejected or approved, we are getting a t-statistic of negative 0.9 and a p-value of 0.34. So the p-value is greater than 0.05. So the result will be that the difference in residential asset value between approved and rejected loans is not statistically significant. So what does it mean when you say it's not statistically significant? You can say that there is not enough evidence to conclude that any type of asset significantly determines whether a loan gets approved or rejected. So the next thing that we are going to consider, we are going to use ANOVA, analysis of variance, to determine if there is a correlation between income and asset value. So the first thing under this analysis that we are going to do, since we are going to compare the assets and the income, we are going to extract these values into new variables. So what we are doing, we are extracting the values in the respective columns into new variables. So after this, we are going to perform the one-way ANOVA. So performing the ANOVA, by this we are going to determine the F statistic and the p-value. So we are using the function F one-way ANOVA. So after this, we are going again to print the F statistic and the p-value. So the first thing that we are going to do is create a hypothesis. So in our null hypothesis, we can state that there is no relation between asset value and income, while the reverse will be our alternative hypothesis, which states that there is a relation between asset value and income, that there exists a relationship between asset value and income. We have said that if the p-value is less than 0.05, we're going to print a statement saying that there is a significant influence of income on the asset value. So if our p-value, the p-value will be less than 0.05, we're going to print out a statement indicating that there is a significant influence of income on asset value. So when we run this, we get an F statistic, and we also get a p-value of 0.0. And from the statement, we can say that there is a significant influence of income on asset value. So from the results, we can suggest that there is a statistically significant relationship between income and the asset value. We are going to reject our null hypothesis, and we are going to accept our alternative hypothesis, indicating that there exists a relationship between the asset values and income. So another correlation that we are going to calculate is the correlation between income and loan amount. We are determining if there is a relation between the income of individuals and the amount of loan they are allowed to borrow. So the first thing that we are going to do, we are going to unpack the data from the columns income, annum, and loan amount. So after extracting our data from the income annum column and the loan amount column into income and loan variables, we are going to perform an independent t-test, and we will be setting our variance to be, for this case, we'll be setting it to be true. So we are going to print the t statistics and also the p-value. And after we have printed the t statistic and the p-value, we can set our hypothesis such that our null hypothesis will show that there is no significant relation between the income and loan amount, while our alternative hypothesis will state that there is a significant relationship between income and loan amount. So to justify our hypothesis, I'm going to use the conditional statements. So that means that if the p-value is less than 0.05, we'll print out a statement saying that there is a statistical significant difference between loan amount and income per annum. While if the p-value is greater than 0.05, we'll state that there is no statistical significance. There is no statistical significant difference in loan amount and income per annum. So when we run this, we get a t-statistic of -69, while the p-value is 0. So the p-value is less than 0.05. This indicates that there is a statistical significant difference in loan amount and loan and income per annum. We can represent the correlation between income and loan amount using a box plot. We are going to first specify the data that we will be handling. Then after this, we'll go on to create the figure. So I'll be using the matplotlib library. So with this, I'm just setting the size of our figure and setting the axis. So I'll be using this function to create our box plots, and I'll supply in the arguments. So the arguments will be income. Income is just a variable that after unpacking our data from the income annum column, we are going to store in the income variable. So I'm just going to specify the data from the income variable, and also the data from the loan variable. So this should be in brackets, meaning it's a tuple. So then we are going to provide labels. So the labels will be the names. So we'll pass in the names of our labels. So the labels will be, let's say, income per annum and the loan amount. So those will be our labels. Then after this, we are going to set the labels, chart labels. So those will be our X labels, the Y labels, the title, and finally we display our figure. So we need to, this is the box plot, which is representing the income and loan amount. So earlier on, what we discovered is that there is a statistical significant difference in loan amount and income per annum. And from our box plot, the box plot representing income per annum is quite small compared to the other one, which is representing the loan amount. The whiskers, so the lines extending from the boxes, are also significantly different. And the median line, the line that you are seeing crossing the boxes, they're also significantly apart. So with this chart, you can see that there is a significant difference between income per annum and the loan amount, which is the results that we actually got when we conducted the t-test between income per annum and the loan amount. You might decide to do away with the t-test and just directly plot the box plot to visualize your information. Output of the box plot, you can be able to assess if there is a significant relationship between any two variables that you are testing. So moving on, I wanted to perform a chi-square analysis where we will be determining the correlation between loan status and the number of dependents. For the chi-square analysis, the first thing, in a chi-square analysis, you need to create a contingency table. I'm going to create it using the pd.crosstab function. So this function cross-tabulates the loan status and the other column, which is the dependent levels column. So after this, we are going to perform the chi-square. So that means we'll be determining the chi-square value, also the p-value from that analysis. Other things that you can determine the degree of freedom and the expected. They are not necessary for this case, so I won't be too much concerned with that. So this is the function that we are going to use to perform a chi-square test of independence. So what it does is that it takes the contingency table as input and returns the chi-square statistic, the p-value, also the degree of freedom, and the expected frequencies. So the contingency table will be the input in our function. We can then print our result. And after we perform the chi-square, we are going to check if the p-value is either less than or less than the significant level. Our alpha will be 0.05. So if our p-value is less than alpha, we are going to print that there is a statistically significant relationship between loan status and the number of dependents, or else we can say that there is no statistically significant relationship between loan status and the number of dependents. So when I run this code, we can see that we are getting a chi-statistic of 1.1 with a p-value of 0.5, and the degree of freedom for our analysis is 2. So from the result, we can state that there is no statistically significant relationship between loan status and the number of dependents. What we will be doing in the logistic regression, we are going to build a predictive model that takes loan application features, the input, and predicts the likelihood of a loan being approved or rejected. The logistic regression serves as a predictive tool, so it will be using the loan application attributes such as the income, self-employment, education, the number of dependents, the CIBIL score, residential, the asset values. So the first thing that we will do in the logistic regression, obviously we won't be using every column because some of the columns were just an extrapolation of the data that we have. Those are the CIBIL ratings column, the income levels column that we had. So the first thing that I'm going to do is going to convert categorical variables into numeric values. For example, in the education column, so I'll be equating that if an applicant is graduate, I'll be assigning them value 1, and if the applicant is not graduate, I'm going to assign a value 0. So I'll do the same for the self-employed column and also the loan status column. While converting these categorical variables into numeric values, I'll be using a function. Let's start with the education column. So the first thing that I'm doing is I'm defining my function, labeling it as edustatus. If status is equal to graduate, then I'm going to return a numeric value, let's say 1. And if status is equal to not graduate, then we are going to return a value 0, else we are going to return a value unknown. So I'm going to close off my equation. So when I print, just a sneak preview to see if we have successfully created a new column, and run this cell, and as you can see, we have created a new column and populated the new column with the values either 0 or 1. We are just going to repeat the same. Now, for the self-employed column and the loan status column, because we will just be repeating the same thing, we are going to encode the values in the self-employment column. That if employment is yes, we are going to return a value or assign a new numeric value to 1. And if the employment is no, we are going to assign a new value which is 0. Then after we are done, we are going to apply the new function while targeting the self-employed column and save our output in a new column, newly created column, that is the employment type column. So when we run this again, you can see that we have created the employment type column with our new and populated it with our new values. So we will just apply the same for the loan approval. So again, when we run, you can see we have created a new column, loan approval column. So this is the loan approval column. So the next step in our logistic regression will be separating the x-axis values and the y-axis values. When separating the x-axis values, so what I'll be doing is that I'm going to drop the columns that won't be necessary. So these columns will be the loan ID. Also, other columns that we will be dropping will be the columns between CIBIL rating and the dependent levels. The loan approval column, we don't want it to appear on our x-axis, so we will also drop it, as well as the loan status column. We'll also drop this. Other columns that we will be dropping is because we have encoded the education column and the self-employed column, so we are also going to drop these two columns. When we drop these columns, let us see what we are left with. As you can see, so generally, we only have numeric columns in our x-axis. So the columns that we will be using on our y-axis, so that will be the column loan approval. So this column will be on our y-axis. And let's see what we have on our y-axis. So when I run this cell, you can see this is a tabulation of what we have on our y-axis. We have defined our axis, the y and the x-axis. So I'm going to import the modules that we will be using in our analysis. So these are the modules that we will be using in our analysis. We will be using the logistic regression module. Also, we'll be using the standard scaler and the train test. The train test split. We're going to split our data. So we are going to split our data to test and training data sets. So with this, we are going to use the train test split as our model. So x and y, these are used to represent our features. That means the input variables, target output variable respectively. So x contains the features, the input features, while y contains the target values. So we have set our test size to 0.3. This parameter specifies the proportion of the dataset that will be allocated to the testing set. So in this case, 30% of the data will be used for testing, while 70% of the data will be used for training. So the X train, the X test, the Y train, and the Y test. So these are variables that hold the resulting split datasets. So the X train contains the features for the training set. The Y train contains the corresponding target values for the training, while for X test contains the features for testing set, and Y test contains the corresponding target values for testing. So generally, when we split our data into training and testing sets, we are able to train our machine learning model on the training data and evaluate its performance on the testing. So for the X train, we are using 2,988 rows and 11 columns, while for X test, we are only using 1,289 rows and 11 columns. The next thing that we are going to do will be scale standard scaler. So I'm going to recall the standard scaler. Then I'm going to scale the X-train data as well as the X-test. Scaling process, what it does is that it centers the data around 0. So after scaling our data, we can then train our model using the logistic regression module. So we are using a random set of 0. Then we are going to fit the X-train scaled data and the Y-train. During this step, the logistic regression model learns the relationship between the features in the X-train scaled dataset and the target variable Y-train. So based on this training data, the algorithm adjusts the model parameters to minimize the differences between the predicted outcomes and the actual outcomes in the training data. So you're going to predict the target values, that means the class labels of the training data using a trained logistic regression model. So log. So what we are just applying the predict function to our X-train scaled data to our training data set. In this case, when predicting, the logistic regression model applies its learned coefficients. It is computing a prediction for each sample in the X-train scaled data set. And the prediction are binary class labels, typically 0 and 1, which correspond to the predicted negative and positive classes respectively. So 0 means a rejection, while 1 entails approval. So we have trained our model and we have predicted our model. Now we can then move on ahead to test the accuracy of our model. So we are going to calculate the accuracy of the trained logistic regression model on the training data, scaled data. So with this code snippet, what we are doing is that it is being used to calculate the accuracy of the trained logistic regression model on the training dataset. And when you run this, you can see we are getting a value 0.92, which is about 92%. So the score method uses the trained logistic regression model to make predictions on the provided on the provided data. It then compares these predictions with the actual target values in the Y-train and calculates the accuracy of the model's predictions. So from the prediction, you can see the accuracy is about 92%. So generally, this accuracy is usually defined as the ratio of correctly predicted instances of the total number of instances in the dataset. So earlier on, we were training our dataset. Now that we have trained our dataset and determined its accuracy, we are going to apply it on a new dataset. So using the test data. So when you run, you can see that when applying on our model, we are getting a score of about 91%, which means that the logistic regression model is achieving an accuracy of about 91% on the test data. By that, we can say that our model is correctly predicting the class labels, either approved or rejected, at around 91.3% of the instances in our test data. In case that the model is correctly predicting the class labels, that means the approved and rejected classes at around 91% of the instances in the test data. We have now reached the end of our video. I'm very glad and very thankful that you have stayed with me until the end. It's been a rigorous exercise with this type of analysis. However, we are very glad to reach the end. I hope you grasped some ideas about this analysis that are going to help you. And before I close off, please hit that subscribe button. Consider subscribing to our channel. You can also give this video a thumbs up and also leave a comment behind. Thank you for your time, and until next time, see you.